So yes, I'm here to talk about Sparc Technologies. So we're a bit of a different flavour from the resource plays, and I'll focus on our hydrogen division in this talk today. This is our corporate information, but I might leave that for people to read in their own time. We did release this presentation to the ASX this morning. So a little bit about Sparc and how we came to be. So we're essentially a company of two halves. We have a graphene materials division and we have a hydrogen or renewable energy division. We started out through IP from the University of Adelaide in graphene and graphene materials, and we're still working in that area today. And part of that work with the University of Adelaide actually led to an opportunity to invest in the Sparc Hydrogen project, which is now, a really big focus of the company and really driving our performance to this day. So to touch on Sparc Hydrogen, we've got some key highlights again. It's a bit of a wordy slide that I might leave people to read in their own time, and I'll cover all of those as I go through the deck in this presentation. So one thing I like to start off with to general audiences is that green hydrogen is often talked about, but what some people don't realise is that there is a market need for it today, and that is to decarbonise the existing hydrogen production industry. And hydrogen, is a 95 million tonne per annum industry today, which is, 4 times the copper industry in terms of volumes, and significant on any measure. So what we're looking at is an alternative way to produce green hydrogen, and I'm really excited to present the project in these slides. But the requirement to decarbonise this industry is significant. It is a hard-to-abate industry in its own right and produces emissions about equivalent to the entire aviation sector. So there is an existing need for green hydrogen. The challenge is producing it in a cost-effective way so that the industry is incentivised to change the production methods that they currently use. And then you've got the blue sky of all the other potential uses for green hydrogen in other hard-to-abate industries like steel making, fertilisers, chemicals production, etc. So currently the green hydrogen industry is really an electrolysis industry, which for the uninitiated is using electricity and vast amounts of it to split the water molecule into hydrogen and oxygen. Now this is actually old world technology. It's been around for 100 odd years, and it's only been in the last handful of years where people have thought about it as a way to produce hydrogen as a green fuel. But there's a few issues with that method. And the key one is the use of power. So it's a very power-intensive process. And with the cost of power where it is today and has been over the past few years, it's really difficult to get green hydrogen to a point where it is economically attractive for people to adopt it unless power prices fall really significantly from where they are today. Now, look, I'm not an energy market expert, but I'd be willing to bet that we're not going to see power prices fall, from where they are now to a third of that in any short period of time. And therein is the opportunity for companies like Sparc in what we're looking to achieve with photocatalysis. The other key thing I like to point out is that these electrolysis projects are typically really large scale. And that is because you need to have that scale to reduce the costs down to something that is approaching commerciality. And for those large-scale projects, you need high-voltage electricity infrastructure, things which require a really long lead time in terms of permitting and the like. So beyond just cost, there are other barriers towards or headwinds facing the electrolysis industry. So what we see as the future for producing green hydrogen is using an alternative method called photocatalysis. So photocatalysis is a method which does not use electricity to split that water molecule. It actually uses the action of a photocatalyst material. And I'll show you a short video on that on a subsequent slide. It's a really simple process in that we're not looking to convert solar energy into electricity and then electricity into hydrogen. We're doing that in a single step. It's a green method as well, with solar energy being the input to drive that particular reaction. And one unique thing that Sparc Hydrogen is really focused on is developing photocatalysis with a scalable and modular reactor where you can actually take this technology from the lab into something that people can use in a commercial fashion. So this is a little bit about our mission as Sparc Hydrogen, and it really is to develop photocatalysis into a commercial industry. And that goes to all the opportunities that abound if you can do this in a commercial way. Our technology and our IP sits in our unique solar reactor, which goes to the modularity and scalability of our system, which we believe will really accelerate, bringing photocatalysis out of the lab into a commercial sphere. So we are a partnership in Sparc Hydrogen. So Sparc Technologies is the majority shareholder at this point in time, and Fortescue, who you'll be familiar with, sits as a 20% shareholder, with the University of Adelaide holding the balance of 28% in recognition of the IP that was developed at the university in advance of the joint venture coming together. Now, Fortescue's been in the headlines, relatively recently about their work in green hydrogen. And one thing I do like to stress is that the reason for their pullback, when you look through it, is really due to the cost of power and those projects really not making sense, those large-scale electrolysis projects really not making sense at this point in time. But one of the prior presenters here, Hytera, they received a $22 million investment from Fortescue looking at an alternative method of producing the same thing, the hydrogen molecules. So Fortescue are not rowing back from hydrogen as an industry, far from it. But if anything, they're diverting more attention and focus on their research and development work streams, of which we form part of that team. So this is a little video playing here on the screen which demonstrates photocatalysis and our unique approach to it. So there's nothing special about this setup here. It's basically a photocatalyst material sitting in a beaker of water. And what we have there is increasing solar concentration on that material. And as you'll see, there's increasing bubbling off of that material with increasing concentration. Those bubbles are hydrogen and oxygen gas. So this shows the simplicity of this process. It's a direct solar to hydrogen process where you're converting solar energy on that photocatalyst material into energy in the form of hydrogen, which you can then use and store just in the same way as you can do with hydrogen produced from electrolysis, for example. So we are taking this principle effectively out of the lab into a modular and scalable reactor, which utilises concentrated sunlight. And I'll show you a picture of that on a subsequent slide. But that's important for a number of reasons. One of those is that if you consider that principle at scale, if you were to have photocatalyst materials laying out under sunlight, you would be splitting water at that relatively low level, at that 1 sun level. But you'd need a lot of photocatalyst material to do that. Here, we're looking to use effectively mirrors to concentrate that same amount of solar energy onto a smaller photocatalyst area, and thereby reducing the use of these materials, which at the nascent stages of the industry are not going to be cheap. So you want to reduce that as much as possible. It also allows us to utilise existing scalable mirror infrastructure, and we're looking to do that with our linear Fresnel system, which, as I said, I'll show you over the slide. And what it also brings is the ability to produce heat. We're effectively heating water in our reactor, and that heat can be used as a byproduct for industrial uses. So there's a few key benefits as to why effectively incorporating principles from the concentrated solar industry with the nascent photocatalysis space has real benefit, and that's where our IP really sits in this particular venture. So in terms of where we're at today, we have prototyped our reactor at the CSIRO Energy Centre in Newcastle. That work was completed in April of this year, and we were testing a reactor which was a sort of square format reactor, not particularly huge, but it was sitting up on that tower in front of those mirrors at the bottom of the slide. And if you look closely, you can see some of those mirrors are tilted up towards that tower. They're the active mirrors effectively concentrating the sunlight onto the receiver there. So that really de-risked the technology. It was the first step out of the lab for the tech, and it worked really well, particularly in the second round of that particular prototyping exercise. And we were supported with some grant funding for that from the Australian government, along with the CSIRO. So the next step for what we're looking to do is to take that into a pilot plant format, and this pilot plant is now set to be located up at a campus of the University of Adelaide, north of Adelaide, and that will be demonstrating our modular and scalable reactor technology, which is taking that square prototype format into a linear Fresnel mirror array. So we're in the FEED study at the moment for that particular plant, and we're looking to complete that sometime around November, which will then allow us to start, hopeful construction and operation early-ish in 2025. This is what a future plant could look like utilising this particular technology and this infrastructure. So this is a linear Fresnel field in Spain, which I visited. And what you can see there is very long rows of mirrors. Those mirrors are about 1 kilometre long, and they're side by side in about 16 rows. And what they're doing is shining sunlight basically up into that central receiver on the right-hand side as you look at it on the screen. And that's producing heat, which they're then converting to power. So we're effectively looking to replace that central receiver with our photocatalytic water splitting receiver, which is a long-winded way of saying that's where we incorporate the photocatalyst material with the sunlight and the water to produce the hydrogen and oxygen. So a really neat system, and once we demonstrate this at the pilot level, to make a system bigger is literally bolting these mirrors together. So we think that's a real advantage as a new technology. And this just goes to, I guess, really drive home the point that simplicity drives the potential for low costs. One of the reasons why electrolysis is really expensive is that you have to go through a two-step process. Photocatalysis, as I mentioned earlier, is a single-step process where you're directly converting the solar energy into hydrogen energy, which you can then use and store. The other advantage I think this tech really has versus the incumbent is that it has really broad use cases. So if you consider that we're not using the same amount of power, it really opens up the potential to use this to produce hydrogen in remote locations. So, mining and oil and gas industry in Australia, remote power is used widely. And this is a potential early adopter of this type of tech, and potentially why Fortescue saw the potential in it a couple of years ago when we invested. The other reason, I think we hold an advantage as we scale is that it is truly scalable and modular in its format. So with an electrolysis plant, you basically try and build it large. It's very difficult to scale from there because you've invested in all the electricity infrastructure that goes into those plants. And then there's a potential byproduct play here with the industrial heat and using that as an energy source for industry. So the green hydrogen race, is on. Going to the point I made earlier, I don't see the costs of electrolysis projects coming down anytime soon. Yes, I'm sure some will attract subsidies, which will help the industry develop, and we're certainly keen to see that as well. But I think there is a real reason to look at alternative tech in this space. And from a personal perspective, I think this is, the really where more funding should be going, given the potential that it holds. I will touch very quickly on our graphene side of the business for those that have followed the company for a while, and it is a longer-standing technology area. And just quickly to say that we have developed a graphene-based additive product which is called EcoSparc. It's very relevant to the oil and gas industry, among others, in that it is used as an additive into protective coatings which go on steel infrastructure. So these protective coatings are used to inhibit corrosion in order to maintain assets more effectively. So we've done a life cycle assessment on the product, looking at a few different pieces of infrastructure, one of which was a wharf, and we've shown that by a relatively simple inclusion of a graphene-based additive, you can really multiply the return on investment for infrastructure owners through the use of that additive and extending the lifetime of maintenance events, between maintenance events, I should say. And then just to quickly say, we've got some field trials underway with the South Australian Government, along with 29 Metals here in Western Australia, and we're targeting some additional field trials with the mining and oil and gas industry, which we hope to say more about relatively shortly. We're obviously also working with the paint industry to get this graphene-based additive into the market, and we're having some really positive feedback there from that particular industry, which is a large industry and a large carrot if we can get this product to market. Thank you very much.